Hi class, today we're going to do some experiments with levers. So this first video we are going to work on first order levers. So you should have your experiment levers and force page out in front of you, and at the very top you will see a little box that says hypothesis, which will have least effort. So I'd like you to make a hypothesis looking down across this page. Tell me which of the order levers you think will have the least amount of effort needed to be put in to move the bucket. Okay, we'll be working with this old scrub bucket today. Okay, and so if you need to, pause the video, look at the paper over, and get your hypothesis written in there. Otherwise, we're just going to get that paper moved out of the way and our arrow moved out of the way, and we're going to pull up some of the information from our note sheet. Here at the top of the page, you'll probably see this formula, and this is the force in is equal to the R, which is the weight, times the distance to the load, divided by the distance to the effort, or in our case, the pull scale. Okay, so that's the formula we'll be using for this experiment, and the definitions there of the things that we'll be finding today. So let's go ahead and take a look at this first one. First order levers is what we'll be dealing with, and you can see we are going to set up an experiment just very similar to what the boy is doing. We'll be using a sawhorse with a fulcrum on it and a board, and we will be lifting a bucket. So the first thing that we need to do for our experiment today is come up with the DE and the DL. So DE is the distance to the effort, okay, distance to our pull scale, and the DL is the distance to the load. So that's the first thing that we're going to want to figure out. Okay, so let's take a minute and measure that. Here with my fingers and bring it down to the, turn that around for you. So right there you can see it is 3 feet. Okay, so from the fulcrum to where we're going to hook our bucket is 3 feet. Okay, so you can go ahead and fill in that 3 beside your DL, the distance to the load. Now we're going to measure the other side where we're going to pull. And here you can see it is 5 feet. So go ahead and fill in the distance to the effort force, 5 feet. Okay, so those are the two measurements that we will be needing for our formula. The next thing there that we see is the R, and the R is the weight of our object that we will be lifting. Okay, so we'll get out our pull scale here, and we're going to go ahead. It is set to kilograms and zeroed out. We're going to go ahead and lift our bucket here. Alright. Okay. And you can see it is 4.5. So we will be using 4.5. It is 4.52 actually, and we will be rounding it to 4.5. So that is what we will be using for our bucket. Okay, now something we need to consider is we must subtract the mass of the extra on the long side of the board. Okay, and if we know that the longer side of the board, okay, the distance to the effort is 5 and the distance to the load is 3, then we realize that there are 2 extra feet on that side of the board. So, if we take a look at this, okay, here on this side is our short side. Okay, this is our shorter side, and this is 3 feet. On this side, we have 5 feet. Now, the problem that we have with that is that if we only had 3 feet on that side and 3 feet on this side, then we would know exactly that our pull scale is pulling exactly what we have on this end. However, there's 2 extra feet on that side that has some weight to it. So it's not 3 and 3 even weight, it's 3 and 5, so it's 2 feet extra weight on that end that's already pulling. So we actually have to subtract that 2 feet worth of weight off of our bucket weight because it's already pulling that. Okay, our pull scale isn't going to have to pull that. But the problem is we have to figure out what 2 feet of our board weighs. And I suppose I could go get a saw and I could cut off 2 feet of the board and I could weigh it with my pull scale. However, that might kind of ruin our experiment, so I don't think that's the best idea. I think that a better idea would be to weigh the whole board and then figure out what 2 feet of the board weighs. So we're going to weigh the whole board by picking it up right here in the center. Going to again make sure that it's zeroed out before I start. This is how much mass our board has. So we have 4 pounds of board weight completely. Now, we only need to know how much 2 feet of that board weighs. So if we know that the the distance to the load is 3 and the distance to the effort is 5, the total distance would be 8. And we only need 2 of the 8. So we have here that our board equals 4 kilograms, but we need 2/8 of that, okay? And when you say of something, that usually means multiply. So we have 2/8 of 4. Now we can reduce that fraction 2/8 to 1/4, right? So let's do that. And now we have 1/4 of 4. Well, that's pretty easy. We can do that in our head. If I have 4 fingers and I need 1/4 of it, I am going to have 1. So 2/8 or 1/4 of our board is going to weigh 1 kilogram. Not too tough to figure out there. So now we know that there is 1 kilogram pulling down on that long side before we even begin to pull with our pull scale. So we need to subtract that off the weight because it's already pulling 1 kilogram worth of effort for us before we even have to hook our pull scale to it. So 4.5 minus 1 gives us a 3.5. 3.5 is what we will be lifting with or pulling with our pull scale, okay? Because that board with that 2 extra feet has already done a little bit of the work for us. So we can go ahead now and fill in our R in our box with 3.5. Okay? So at this point, we have all of the things that we need to fill in our formula here. So let's go ahead and do this. We have DL, that's 3. Okay, we have DE, that's 5. And we have our R being 3.5. Now, we're going to go ahead and do the math to see what the force in should be. And then we're going to do the experiment and see how close we come. Okay? So, as I've said before, this is a science class where we want to see the science work. We don't want to make mathematical errors. So we're going to do it on our calculator. So we're going to say 3 divided by 5 equals, we get 0.6 there, and then we're going to multiply it times 3.5. 3.5. And we get 2.1. So it looks like 2.1 should be what our pool scale reads when we do our experiment. Let's go ahead and we're going to see how close we come. Okay? I'm going to hook my bucket up to this shorter end, the 3-foot end, right? Distance to the load was the shorter end, and then I'm going to take my pool scale down and hook it up to the effort end, okay? The DE. Make sure that it's zeroed out. I'm going to pull. Finally got it. And our scale reading is 2.065. And if we round 2.06 to the first decimal, that 6 would make it round up to 2.1. So we got it right on the nose. Our math proved our experiment, and our experiment proved our math. So it worked out absolutely perfect. That is our first video for our first order of levers. All right, so if you need to take a minute and fill in your boxes there, go ahead and do that. And the next video, we'll be doing the second order levers.